water molecule, 70% of the cell is made up of water, and 70% of the earth is covered by this very special molecule, which has very unique properties. The simple structure of a water molecule is shown here, with oxygen having 6 valence electrons, hydrogen having just a 1 valence electron, and H2O being formed like this with 2 covalent bonds. But because of the tendency of oxygen to keep electrons closer to it in the covalent bond, the term for this tendency to keep electrons closer to itself is electronegativity. Oxygen has a greater electronegativity than hydrogen. So the 2 electrons in the shared covalent bond are kept much closer to oxygen than they are to hydrogen. And this allows for the development of small charges at the hydrogen ends, positive charges, and negative charges at the oxygen. So this water molecule takes on this V shape. The molecule has a V shape because these bonded pairs would like to push away from each other as much as possible to create a straight line. But they can't create the straight line because these lone pairs of electrons here push down in this direction. So this is of more relevance to students studying chemistry. What is of more significance in biology is the polarity of the molecule, but we should also look at the shape, and the shape is in the form of a V because lone pairs are pushing against bond pairs. So the molecule would like to have as much repulsion here, but it can't because this is getting in the way and causing the pushing. So the water molecule is V-shaped, but what's of greater significance in biology is that it is a polar molecule. And when it's a polar molecule, what it means is that one polar molecule like this, with its small positive charge, what's going to happen between one molecule and another one? They're going to attract each other. There's going to be a relatively strong force between this and another water molecule that might be sitting out here. There will be another one that can get attracted down here, isn't it? And then there's another one that can get attracted down here with its oxygen. This is a 2 negative charge, isn't it? So it's kind of been satisfied only partially, hasn't it? It's still going to be slightly negative. So therefore another one of these. So one water molecule can form these fairly weak bonds. They're not as strong as covalent bonds. But they're bonds not inside of a molecule, are they? They're bonds between one molecule and another molecule. So it's a bond at the molecular level. Intermolecular bonding between one molecule and another one. As opposed to intramolecular bonding, which is inside the molecule. It's between one molecule and another one. And while there are many different bonds to study about in chemistry that hold one molecule to another one, this type, called the hydrogen bond, is very strong. It's the strongest one between one molecule and another one. And water is something that's...
Wait, sir, you just said that these are not such strong bonds.
That is a very good point. That's a good point, Rehan. It's not such a strong bond when compared to a covalent bond. Okay? So, it's like a high school team won championship in a sport. They're the best team in the high school league. What are you going to take them and put them up against a professional team? Then suddenly they become very weak. So, where bonds between molecules are concerned, hydrogen is the strongest. But when you compare that to the big league of bonding, which is ionic bonding and covalent bonding, the bonds that happen inside of a molecule, those are really strong bonds. So it's weak compared to those, but where the bonding is between one molecule and another one. Intra is within. So you have intramolecular, which is within a molecule. Inter is between, relatively difficult to break it, compared to like other molecules. And the molecule that we are going to compare it to is methane, CH4. Compared to methane, the bond between this and one of its neighbors is so weak compared to this. And the reason is because carbon is not as electronegative as oxygen. And this molecule is not a polar molecule by any stretch. So therefore, there's not going to be any strong hydrogen bonding between one methane and another methane. That is going to affect a lot of its properties.
So you're saying that they're less likely to bond with other molecules.
This is not going to have any strong bonds with other methane molecules like itself. This is going to have a lot of strong hydrogen bonding. This strong hydrogen bonding allows one water molecule to stick together with another water molecule. It allows a water molecule to stick on the surface of my skin. And I could put a drop of water on the surface of my skin and turn my hand upside down and it would stay there. For a while at least. It would stick on certain surfaces. When the water molecule kind of sticks onto a surface because of its charges, its polarity, then you call that. When a water molecule is heated up, it takes a lot of energy to get these bonds broken. Relatively speaking, compared to something like methane. It takes quite a lot of energy that you have to put in there. And when it takes this much energy, we say that the liquid environment has a very high heat capacity. Key to its function as the medium of life. Because if aquatic life is going on, and there's so much life in the ocean, 70% of the earth is ocean. If it were that this ocean could heat up very quickly, then that would be very bad for life. Lakes in the ocean. But it takes a lot of heat during the day for your swimming pool to get hot. It's only by the end of the day of hot sunshine, even in a place like Bangalore when it's really hot, you go into the pool at 10 o'clock in the morning and it's really cool. It's by the end of the day that the pool is really hot. It takes all day to heat up that big body of water. That's just a pool. Imagine if it's the ocean or a lake. It's going to take a lot of energy to heat that water up. So the main source of heating for the ocean is solar insolation. It's going to take a lot. And what that does is it gives life nice, stable conditions to exist in. Life needs to get stability. It needs to get constant internal environment, which is called what? Homeostasis. Life seeks to maintain homeostasis, but in a sense, homeostasis is needed in the external environment also for life to continue to exist. And water facilitates both. It prevents our bodies from heating up too much, even though as people we complain about the heat. We would boil very quickly if we weren't made some 70% water. So this is what makes the water molecule special. It allows it to have a high heat capacity. What about its ability to cohere and to adhere? How is that special for life? It's very special. Anyone can tell me. How is this bit here very helpful? About this
Capillary action.
capillary action. What am I drawing here really? What is this going, this long tube that's going to take? It allows for the uptake of water from the soil to the root. It allows for a continuous column. By cohesion, water molecules stick to each other. They stick to the walls of the xylem. And through cohesion and adhesion, you have the phenomenon known as capillarity, the rise of a column. The transpiration pull. Processes of cohesion and adhesion existing why? Because of hydrogen bonds. And hydrogen bonds existing why? Because of polarity. And polarity existing why? Because the elements that make up the molecule have differences in electronegativity. And when we go into our book and we look at the table and we see how this molecule compares to this one, methane compares to H2O in terms of its melting point, its boiling point, its heat capacity, its heat of vaporization also, the energy needed to go from the liquid state into the gas state. We'll see that water wins by a long margin every time compared to methane. So this is why this is the one that sustains life as we know it, as opposed to this one. This is the molecule upon which life is not built, I should say, because carbon and hydrogen builds the structure of our bodies, and also plants. But this is the molecule that fills every cell, 70%. It fills the environment, and it's required for the sustenance of life on Earth.